let me say a little bit about how MPI interacts with the hybrid programming models. And what do I mean by that? Sort of the combination of several programming models, or maybe more precisely, programming systems in the same program. They might be mixed in the same source code. There might be different combinations of components or runtimes, each of which represents its own well-defined model. Perhaps the most common one is MPI plus threads, or MPI plus a specific version of threads like OpenMP. There are some other interesting choices, including MPI plus MPI. And so why is this interesting? Well, I'll point out it's not new. You're already doing a hybrid programming model because you're using C or Fortran. I don't know anybody who's able to write an MPI code without C or Fortran. And so you're already doing a certain amount of hybrid programming. So we're talking about adding a third to the two that you already have. And that might seem a little disingenuous, but really, they are different programming models. The C and Fortran programming models are how you program a single thread. MPI is how you get the threads to talk to each other. Now we're going to talk about how we program multiple threads together. And so it's really adding that third piece. Well, I mentioned some people feel that they only want to use a single programming system. I think many applications, many workflows right now are built out of lots of pieces, including pieces that use Python. How many people have Python in their workflows? Okay, that's quite a few, right? So you're already doing stuff like this. So adding another programming system in a well-defined way is not necessarily so bad. And there are some really good reasons, at least to think about this. So MPI defines parallelism between processes. And the processes have separate address spaces. So thread parallelism gives you a shared memory model within a process. OpenMP is a very common model. POSIX threads or P threads is another model. In some ways, OpenMP is a little better defined than that because it's really part of the language, whereas P threads or POSIX threads is a library. There's a wonderful article on, I'm trying to remember the exact title. This is like why you can't define a thread library, or that explains why it is, and that if you define a library to implement threads, it can't. Yeah, why threads cannot be implemented as a library. Some of the things that we talked about in shared memory about the problems that you face apply to pthreads library. And the only reason that you say, well, people use threads programming all the time, it's because the compiler has learned not to do stuff with certain pthreads routines. Okay, so, but pthreads do provide a more complex and dynamic, sort of richer approach, although OpenMP with version 4 has added a fair amount of flexibility in terms of dealing with thread programming beyond a sort of data parallel approach. Of course, I used to say all chips are multi-core, but it turns out that they still manufacture chips that are single core, particularly for use in deep space, because they're much more reliable in a radiation-hard environment. But for the most part, anything you see is going to be multi-core these days. And so you're faced with how to program them. A lot of people still program them with what we often call the MPI everywhere approach. So you just put one MPI process on each core and do that. And then use MPI to communicate between the cores. If they're on the same chip, the MPI implementation will, in fact, use shared memory to do that. So the communication performance is quite good. One of the nice things that you get from that is, because you're using MPI and because you're using separate processes, one of the things that the operating system understands is process locality. Operating systems don't seem to understand thread locality very well. This is partly because threads can be used both to divide up work, but also to provide an event-driven approach to responding to operations. In one of those, you want the threads on different cores. In the other ones, you want the threads all in the same core. And the operating system cannot there's no way for it to know what kind of application you are. It might say, oh, I know user Smith, those ones should be spread this way, and user Barry, they should be spread this way. The operating system doesn't know, but processes, it knows. Processes stay on the same core. And that's just the way the operating system looks at it. As a consequence, the MPI everywhere model performs very well because the operating system leaves the process in one place where it can make maximum use of the core, and the poor programmer has been burdened with the obligation to make all that work. So if the programmer does, they're great. Okay. But it does introduce some other things that can impact the performance. So you might want to think about things like MPI plus OpenMP, as we've said, or MPI plus P threads. Those are often what people mean when they say hybrid programming. You can also say OpenACC instead of OpenMP. Again, it's a way of combining these programming systems together. Okay, there are a lot of myths, particularly about the MPI plus OpenMP model. So one myth is it never works. So by never works, I mean never performs well enough for me to use it. And so it gives me the correct result, but the performance is poor. So there certainly are examples, in fact, dating back quite a while, where this model has worked very well, where programmers without too much effort have been able to get enough locality to get good performance from it. Equally true is, or equally untrue is the statement that it always works. So there are lots of examples where people have gone from MPI everywhere to MPI plus threads or OpenMP, and the performance goes down. This is often related again to locality. Managing locality can be difficult, particularly because the thread programming models often provide very limited ability to manage memory locality. So there are a number of examples that you can see for where it has failed to provide good performance. Another statement is that it requires a special thread-safe MPI. This is one that has some shades, but in many cases it does not, particularly in the case where the thread environment is being used to provide some sort of data or loop parallelism. Oops. And the last one is that it's harder to program. And this is sort of like the rest of these. There's a germ of truth in it, but one question is harder than what? Right? So I didn't say it's not hard to program. I mean, MPI can be hard to program, but what are your alternatives? And if you're trying to get performance, how hard is it to achieve your goal? And so as you start looking at how the effort that you have to go into to get performance, to deal with scalability problems, to deal with load imbalance problems, it turns out that taking advantage of threads might be easier than other things that you might be able to do. And then say easy, I said easier. There's a huge difference. Okay. It is important to understand the issues behind this. It's very easy. In fact, I would argue, particularly in the bar, that OpenMP made it way too easy to write a program that performs poorly. But if you apply the right approaches, and you can find some, for example, in this book, using OpenMP, there's a couple of pages, 207 to 211, where they discuss this hybrid model and they discuss some of the issues for performance programming. And I will say, in the interest of full disclosure, as an editor of this series, I get like a fraction of $1 for every copy that's sold. So go out and buy a lot of them. But it does tell you what sort of things to consider as you're trying to get good performance out of a code that has OpenMP in it. Right? And so it's important to be bearing that in mind. Now, for one of those other questions about the special MPI for this, starting with MPI 2, MPI introduced 4 whole levels of thread safety. Now, it's not true that MPI wasn't thread safe before MPI 2. It was, in fact, designed from the very beginning to be thread safe. And with a few exceptions, you'll find a thing called an MPI message in MPI 3 that addresses a sort of odd but important corner case that we missed when in defining an MPI 1. But MPI was defined to be thread safe, but it's actually very hard to build a system that is not just thread safe, but fast and thread safe. And in fact, as IBM was building their thread safe MPI implementation, so MPI, the specification, was thread safe, that didn't mean that all the implementations started life as thread safe. The specification was designed around the notion that it needed to be thread safe. So for example, MPI doesn't have the notion of a current message because as convenient as a current message is, as soon as you have 2 threads, you don't know what that means. And so MPI avoided things that wouldn't have workable meaning in the case that you had more than 1 thread. But as IBM was trying to implement a fast MPI, they discovered that there were various trade-offs that they had to make for performance reasons. And if they knew a little bit more about how the user was going to use the code, they could do better. And remember, I just gave you an example of where, if you could tell the OS how you were going to use the threads, maybe you could do a better job of laying them out on your cores. This is sort of like that for the MPI implementation. So based on what they were doing, they realized you really wanted to have these sort of 4 levels. So thread single is there's only 1 thread, period. Thread funneled is there may be multiple threads, but all of the MPI routines are called by the same main thread. Right? So the main thread is the thread that called MPI init, or MPI init thread. Why is that important? Well, I was talking about these memory, the shared memory issues, and when you know when data is available that you've written to that's in shared memory. In this case, the MPI implementation knows that whatever data was done to update the MPI state, it was done by the same thread that's now running. And that means it needs no memory fences. Why do I need it at all? Well, the MPI implementation might do a malloc. And a user thread might do a malloc, which means that the MPI implementation better use a thread-safe malloc. MPI thread serialized, things are multi-threaded. Only 1 thread at a time calls MPI routines, but it might not be the same thread. Okay, now what happens is the implementation doesn't have to worry about mutual exclusion between the threads updating the same MPI state, but it may have to worry about the memory model and the consistency of the memory image that it sees. So there are a few things that it might need to do that it doesn't need to do in the thread funneled case. And then finally, thread multiple. This is the free-for-all mode. So you got a bunch of threads. They're making MPI calls willy-nilly. That means that the MPI implementation has to be very careful about any updates to its internal state, access to the communication system, and so forth, so that the interactions between the threads don't cause any problems. And so that will have the highest overhead, but then the highest generality. And you specify this by using MPI init thread. So we kept MPI init, but you really should be using MPI init thread. And you request a level of thread safety, and you get told what you got. So this allows you to initialize MPI and discover that you don't have as much thread safety as you'd like because the vendor didn't implement it. And then you can decide whether you want to give up or make do with what you've got. Why did we do this? Well, it would have been great to say that in order to provide MPI implementation, you have to provide everything. It might surprise you to know that we just don't have that much influence. The market for high-performance computing is actually a pretty good size. This is actually the coolest place to be working. But we don't have the kind of power to tell the major vendors, you can't release that and call it MPI unless you do this. And we have trouble, it's hard to get people to put out correct compilers. So we had to compromise here. And the compromise is that we allow implementations to maybe not provide full thread safety, but they have to tell you that. And they have to tell you that in a way you can find out, as opposed to burying it in the manual someplace. Right? So at least you can find out. MPI-CH and at this point, I think most implementations actually take advantage of that runtime control. So for example, an MPI-CH normally is built to support thread multiple, but if you don't ask for thread multiple, there's an if test that skips the overhead of all the mutual exclusion that's needed around parts of the code that can only be run by one thread at a time. And that improves the performance, or it reduces the latency significantly. And the cost of that branch, while non-trivial, is way smaller than the cost of enforcing the thread safety where you don't need it. Okay. So what does thread multiple mean? It means MPI's precisely specified this. So for example, it means that you can call any MPI routine, including a blocking routine, and that will only block the thread that calls it. It won't block the whole process. So if you, for example, you want to have a receive listening for a message, you just put it into a separate thread, let it run. It will not block any of the other threads. It is the user's responsibility to avoid races. So if you have multiple threads that are, say, updating the same MPI structure, they have to make sure they do it in the right order. So for example, say you do a send on a communicator in one thread, and in another thread you free the communicator. It's not MPI's job to make sure that you don't free the communicator before the send has happened. Right? That's your job. So in fact, what does it mean for MPI to be thread safe in this sense? It means that if you take each of the threads and you think about any arbitrary interleaving, so you can sort of take each statement in the threads and put them on a little strip of paper and then you slide them up and down, any sort of interleaving needs to be valid. Right? Now, if you've got a place where the threads do something to synchronize each other, then you can use that as a spot where they all have to get to. But it's up to you to make sure that you don't do things that would cause race conditions. Okay. Another example of a race condition would be calling collective operations on the same communicator. So if I had one thread that called all reduce on CommWorld, another thread that called broadcast on CommWorld, that would be an incorrect MPI program because I wouldn't know, on some processes, the all reduce could happen before the broadcast. On other processes, the broadcast could happen before the all reduce. That's an incorrect MPI program if they're on the same communicator. If they're on separate communicators, that's okay. Okay. So what's the state? So implementations are not required to support anything besides thread single. Fully thread safe will provide thread multiple. Technically, a program that calls MPI init is supposed to only get thread single. So if you write your program with MPI init, you are claiming that there's only one thread in the code. That means that, for example, strictly speaking, you shouldn't use OpenMP with an MPI program that calls MPI init. Instead, you should call MPI init thread with at least MPI thread funneled if you're using, say, OpenMP in the data parallel mode. If you're using it in a sort of task parallel mode where different OpenMP threads might call MPI routines, then you have to use MPI init thread with MPI thread multiple. Okay. Essentially, everybody supports thread single. Virtually everything supports MPI thread funneled. It's mostly because of the way things are built. Yes?
So if I use OpenMP, but like formally in the single threaded part from OpenMP, that's where I do my MPI call. Can I still use MPI thread single?
No, so that's still thread funneled. If you use OpenMP and you only have one thread, that would be okay with MPI thread single. If you use OpenMP and you have two threads and only one thread makes MPI calls, then it's either thread funneled, if it's always the same thread that makes the MPI calls, or thread serialized if it's only one thread at a time that makes MPI calls. And now, so some of you are wondering, but I've done this and it's worked. Yeah, it'll usually work. It may always work. I'm saying strictly according to the standard, there's no guarantee. And it's because the MPI implementation, for example, could be making calls to like malloc that are not thread safe to optimize things, and the OpenMP runtime might be doing something different, and then horrible things could happen to you. In reality, what you found is that most of the runtime environments that have been built have been set up to be thread safe, so this doesn't happen. But strictly speaking, if you use OpenMP or anything else with multiple threads, you should at least use MPI init thread with thread funneled. Okay. Yeah, in most, again, if you're using OpenMP in the sort of data parallel, you've got a loop and it's going to run with multiple threads, all you need is thread funneled. Because, in fact, you make no MPI calls inside the OpenMP section. You're always making your MPI calls in the main thread, which is outside the OpenMP sections. That's the definition of thread funneled. Okay. Of course, if you have to be careful if you do that, because you can you run into scalability and performance problems. Interestingly enough, there's a good match between these four different levels and different ways of using OpenMP. So thread single is essentially there's no OpenMP, or there's number of threads equals 1. Thread funneled, we just sort of talked about, and this might be all the MPI calls, they're outside of OpenMP or inside a master region. Thread serialized is like the MPI calls are inside a Pragma OMP single, right? Because you don't know which thread it may not be the same thread each time, but it's one thread at a time. So that's it. And then MPI thread multiple is, again, the case where you may have multiple tasks, each task in their own thread, each of those tasks making MPI calls. And I think I do need to update this. Some of the things to watch for is that there's limited thread and no explicit memory affinity control yet. There are things like first touch. It's intended to have the owning thread, it performs the first access, and then it gets allocated to the appropriate parts of memory. This is still no good way to reassign memory affinity, so if you have something really dynamic and stuff needs to move, that can be hard to do. This is another reason why some people have found MPI everywhere to work well, because when you move the data, you actually make the copy. You might, copies are usually wasted time because you didn't accomplish anything. But in fact, if you make a copy, you have done something. That is, you have effectively changed the locality. And sometimes that's important. The OpenMP memory model can occasionally require a flush, which is, as is the case for essentially all shared memory programming models, is subtle and difficult to know exactly when you need it. At least it's there, which is great. Some of the things to watch for in MPI plus OpenMP, maybe the biggest thing is we talk about programming models of MPI plus X. We spend a lot of time talking about particular kinds of X. The actual hard part is the plus. The X is pretty easy. People have done that. Right? There's lots of stuff on OpenMP. The real challenge is how these work together. So for example, MPI is using some threads. Maybe it's decided to use one core for communication progress. But it'd be kind of bad if OpenMP looks around and says, gee, I can use that core for the loop parallelism, and I'm using the regular loop blocking, which now means that I have evenly divided the work across cores that have uneven capabilities, because one of them is busy doing communication. And now I will get really bad performance because that one core will hold everybody up. Right? And so the fact that there's no yet defined way to negotiate the sharing of these resources provides a problem. And again, so when you look at the literature and you find places where people say, we tried this model and it's a terrible idea, this is sometimes the reason why. Doesn't mean it's a terrible idea, it just means it's hard to get right. Another question is just how many threads do you run? In some cases, you want to run more threads than you have cores, but not too many more threads than you have cores. And again, will depend on how well those resources are shared and how you're allocating work across the cores. And it's not just cores. It could be memory bandwidth. It can be network access. I'll show a couple of slides showing that there is a difference between the way threads and processes are able to make use of the networks. Okay. It can work well in a lot of places. If you've got enough compute-bound loops, so you've got many operations per memory load, using OpenMP can be very helpful if your algorithm is very latency sensitive. So you write the algorithm taking advantage of threads and shared memory within the node. If you are able to manage locality and some of the other issues, can allow you to get away with algorithms for which the latency of message passing would just eliminate their value. Another thing which can be very useful, and I think is one reason that more people should be thinking about these models is, again, if we think about how performance predictable these systems are, once you face the fact that even though you have divided the work up, you have not divided the time up necessarily evenly, then you may need to move the work around. Okay. In a shared memory system, particularly taking advantage of, for example, task parallel features or certain kinds of dynamic loop sharing, this is pretty easy. Sharing work between processes is more cumbersome because it requires explicitly moving the data. Now, explicitly moving the data does have that benefit that it gives you locality, but it is a significant amount of additional work. And so a thread model with the right sort of tasks can make that easier. The examples that we gave today just don't have enough compute to make this worthwhile. It really needs to be something more serious. A more interesting case, so for example, for those of you that do solve large systems of linear equations using some preconditioned Krylov method, it's quite typical to use a block preconditioner blocked to each process. That's a scaling problem because your preconditioner is different with each, as you change the number of processes. And as you increase the number of processes with a fixed size problem, those blocks get smaller and smaller and smaller, which means your preconditioner becomes worse and worse and worse. One thing that you can do is block not by process, but by node. Okay? You still have a scaling problem because as you increase the number of nodes, your preconditioner will get worse, but it'll be somewhat better because your blocks are bigger. The reason people often don't do that is that the preconditioner that you use inside the block is exactly the sort of case where latency matters. For example, you're doing an incomplete factorization. If you can take advantage of shared memory, fast access to memory, you might be able to more easily build your preconditioners on a node block as opposed to process block size. That can give you not a sort of asymptotic power benefit, but it may give you a constant benefit. A constant benefit may be large enough to be worthwhile. But the ability to move work around, particularly if the way you arrange this is that most work stays in one place so that you get maximum locality, but as you discover that, say, some core is far behind the other cores, you can move data away from that core to cores that have completed their work to time balance the computation on each node. And particularly with fairly large nodes, which is what we're seeing for the next generation of machines, there's a good chance that that the variation between the nodes will be relatively small, even though the variation between cores might be fairly large. Right? It's not perfect. You may still need some mechanism to shuffle data between the nodes, but if you do that with one level, in other words, you just think of MPI processes everywhere, and I do work sharing among all those processes, there's a lot of overhead there. If instead I think of my work sharing, my work balancing as first balance inside the load, and then as necessary balance between the loads, I have organized my algorithm in one place where I've got really fast communication. I've got hardware support for shared memory, so hardware support for communication, and then smaller amounts of data that I might be moving between nodes rather than between processes. And so this is another reason to think about a hybrid model that allows me sort of access to the shared memory like that. Where is pure MPI better? Well, turns out because of these locality issues for performance, you often end up writing code that looks a lot like MPI code, even if you're using some other programming model. And so in some cases, you lose the benefit of having that threaded model because you have had to do so much to maintain that locality. Another reason is that you may discover that while too many MPI processes might saturate the network, one process isn't enough. And in fact, we saw that with the Cray. Right? One process could only manage about 3.6 gigabytes per second, or a little more than half of the bandwidth of the network. So if I just had one MPI process communicating, again, that communication would be running slower than it could run, making maximum use of the interconnect. So I might need to have 2 or 4 MPI processes in order to make full use of the network. In addition, and though this is old data, but recent data that we've looked at has shown similar behavior. On many systems, if you have what looks like the identical case, so top and bottom, I have 4 threads here communicating to 4 threads here, and I have 4 threads here communicating to 4 threads here. The only difference is these threads are in the same process, and these threads are in 4 different processes. But otherwise, everything is the same. And so you'd like the communication performance to be the same. You'd sort of expect that. But in fact, sometimes and sometimes not. So in these cases, the case of 4 threads in the same process was significantly slower than 4 separate processes, 1 thread per process. Here, they were more or less the same, except in this one case when there were the maximum number of threads per core, 1 thread per core on that hardware. And so just because it seems like you should get the same performance, again, you have to check. You have to understand where that is. And then finally, if you're trying to make this work, you really do have to be careful about locality and the placement of the processes and or the threads on the node, and that does impact the communication performance. And so we can look at sort of example here. If I've got 8 processes. I put them in a mesh. How should I match them onto a single node? Well, I could do it by round robin, which I've done here. And what that, so if I do that, so I put one process here, then I put one process in the next chip, then process and process, 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 which is, it's sort of nice, right? It takes consecutive processes and scatters them out among the hardware, right? But if your communication pattern has processes talking to their neighbor, what I have here is I've got this process sends data to its neighbor here, this process or there, so it goes from 0, 1 to 1, 1. These are now numbered as if they were in the mesh. I've got 2, 1 goes to 3, 1. I've got 1, 1 goes to 2, 1. I've got 3 times as much data moving between the chips as I would have if I put the first process here, the second process there, the third process there, the fourth process there, the fifth process there, the sixth process there, the seventh and eighth. Right? So that layout, again, it's not a small effect. It's 3 times the communication between the chips because I laid it out that way. Right? So it's important to bear those in mind as you think about how you make use of these SMPs. Okay. Then maybe the last thing is how do you organize the code? There's a fine-grained approach and a coarse-grained approach, and of course a spectrum in between. In the fine-grained approach, the program is single-threaded, except when you're actively using multiple threads. So this is like you write a single-threaded code, and then you have a loop, and you make that like an OpenMP loop. Nice thing about this is that you basically have a single-threaded program, which is easy to reason about. And in the places where maybe you're doing a lot of work, you bring in extra threads. So you have a fairly easy to read and understand code. And if you're starting with a single-threaded MPI code, you can make it multi-threaded quite easily. However, there are a lot of disadvantages to this. Just managing those threads, good implementation, they'll get created once and then what they call parked, but they still have to be restarted. You have to manage them. You've got locality issues you have to worry about. In particular, you may find that if you initialize the data structure set on one thread and then have a bunch of threads work with them, the data will not have the right kind of locality for good performance. And then you've got the Amdahl law problem that you've got a lot of serial code that's going to limit your possible speed up. In the coarse grain model, you basically like do an MPI init, and then you do a OMP parallel, and then the entire code is inside a parallel section. Pros of that are you minimize the overhead of using the threads. You minimize, in some sense, the problems with locality because every place that you're touching data, including initializing it, is already multi-threaded. And it forces you to be thinking parallel the whole way, which is often a good thing. The downside is that multi-threaded programming, even with the sort of data parallel support that you get with OpenMP, is not easy. It's very easy to make mistakes in terms of shared memory access that can be hard to track down. And since the whole thing is like this, there are no sort of obvious places where you can say things should be nice and consistent here. Okay, and then let me just say briefly, there are a lot of interesting challenges here in trying to solve these problems. Again, as I mentioned, that plus is actually the real challenge. It's very easy to define these different programming models. Making them work together well is a hard problem, and one which I think even today is still not getting enough attention. So for the computer scientists in the audience, I have a research topic for you. And so I hope to interest you in that. It's also important for these programming models to provide clean ways to share data. So that's also part of the coordination, but has more to do with how they interact with the programmer and how you interact with the data. And it's pretty easy to come up with ways to do this that are nice and robust and easy to use. When I add fast, it gets much harder. So it's one of those engineering adages that you can have it fast, on time, and cheap. Sometimes they say pick 2. Often we say pick at most 1. In some cases, you get to pick 0. Those are interesting and challenging problems. Sharing the communication infrastructure is something that we're seeing a bit more of. We've looked at various pieces. The vendors are starting to build their own sort of shared infrastructures. So IBM has done that with first Lappy and then PAMI and then some successors. Cray has its own system that it's putting together in which it's supporting MPI and some PS languages like UPC and things like Chapel. And so even though there isn't, say, a portable version of this, we are starting to see the emergence of systems that allow you to build a code that might have co-array Fortran routines in one part, MPI in the other part, UPC in yet another part, and have those all work together in some sensible way. But that does mean thinking about what does it mean to have an MPI program with processes calling co-array Fortran routines that have, or Fortran has its own notion of what is a operative task, and including, say, UPC, which has yet another notion of what is a task. So again, the challenges are figuring out how to make all that come together. So in conclusion, let me just sort of say that hybrid programming does have some advantages and strengths. It can provide you a way to solve problems that you have, particularly if you find that you're suffering from certain sorts of strong scaling limits. So being able to use a threaded model can reduce the impact of those, provides ways to deal with performance irregularity. I try not to say load imbalance because you may have perfectly balanced your load, but that doesn't mean you perfectly balance the time. So it may provide you the right sort of things to allow you to balance the time. And I think that as we go forward, the very real problems that exist now in terms of how do I define the plus will be solved.